This is video 3.4 on parabolas and some applications of parabolas. We use the shape of a parabola in different applications. For instance, in an antenna, the radio signals will hit the dish and bounce to the focus, so that no matter where it hits in the dish, it always goes to the focus. This would be where you would put your transmitter. And so what we're going to look at in this video are several applications, work a couple of examples, but keep in mind that there are many, many applications for parabolas that we see all around us. Okay, as I'm filming this, or as I'm recording this video, the Olympics are going on, the Winter Olympics in Sochi. And so I found this, and this is an actual real thing. This is how they light the torch. I mean, you would think, wouldn't you just use a match? But they actually use a parabolic mirror, and that's what this is here. So once again, the sunlight comes in, hits the parabolic mirror, and goes to the focus. And when this lovely dressed woman puts the torch right in the focus area, all of that heat is directed right at the torch, and that's how they light it. It's kind of interesting. So anyway, you can take a second to read this, but I thought it was very timely. Now, something that is a part of a parabola that we've not talked about up to this point is the Latin word latus rectum. I know, laugh, that's fine. But what it does is it controls how wide the parabola is opened. And the latus rectum is just a segment that passes through the focus. So it's an actual length, and the focus is down the center. So the latus rectum is the length here. It is also determined to be 4 times A, or another way of saying that, it's the length of 4P, which kind of makes sense if you think about it, because 4P is going to determine in a parabola, 4P is going to be equal to 1 over A, and A determines stretch or shrink. So 4A is going to actually tell me this, or 4P. In this diagram, they use the letter A, but it's the distance from the vertex to the focus. So this segment right here is the latus rectum. Okay, so here, if you'll copy this down, take a second to copy this down, we remember that the standard form of a parabola is x squared equals 4py, and that's one where the vertex is at 0, 0. Vertex form of the same line is going to be ax squared plus y. And so if you look at this, the position where 4p is would be actually 1 over a. So 4p is equal to 1 over a, or a is 1 over 4p. So here are the relationships. These are really important. And then what we're going to do is we're going to fill in this chart and find all the pieces and see how they are all related. Okay, so we have p equals 1, 2, 3, and 4. P, remember, is the distance from the vertex to the focus. We're going to have the equation of the line. We're going to find what 4p is. We're going to write that in vertex form. We'll find A. We'll also find the focus, where the length of the focus is, and from that we will find the latus rectum, and that's LR over here. We'll just call it LR. It's hard to see, it got chopped off, but that's LR. Okay, so for P equals 1, the equation is going to be x squared minus equals 4y. 4p is just 4 times 1, which is 4. The vertex form, if I know what 4p is, right, then I know that a is going to be 1 over 4. So the equation will be y equals 1/4 x squared. A is 1/4. The focus is going to be p away from the vertex, and so this is just going to be the 0.01. And so the latus rectum then is going to be equal to 4 times A, so 4 times P, sorry. And so that will be the same, this is 4 times P, right? So the latus rectum will be 4. Okay, so if you work these down as a column, you can see that you have x squared is 8y, you have x squared is 12y, and x squared is 16y. And so 4p is 8, 12, 16. So that would make this 1/8, 1/12, 1/16. And so this would be 1/8, 1/12, and 1/16. The focus is just 0, 2, 0, 3, 0, 4, and then the latus rectum is the same thing as 4p, right? So we see the relationship between 4p and A. We see the relationship between 4p and the latus rectum. We see the relationship between the equation written in standard form and the equation written in vertex form. So this screen allows you to make some observations, so take some time to do that so that you can see the relationship between all these pieces. This is just for fun. I wanted you to see the three-dimensional versions of parabolas. One of them is, these are called paraboloids. This one is just a three-dimensional. This one is just a three-dimensional, so it's like a parabola rotated around an axis. This one is more four-dimensional. It's kind of a saddle shape, but it's called hyperbolic, and it has actually 4 dimensions instead of 3. And so it's just really unusual, and I wanted you to look at them. The last 2 screens here are problems that we're going to use. This one is about solar energy. And so what you're looking at is a story problem. Now you're probably asking yourself, what on earth do I have to write here? What I would write is the word solar energy, and then I would take a second to draw the picture. Notice the parabola. This is the boiler. And then here's the depth of the parabola, and then from here to here is 37 feet. So two of the things you have to find, we're going to write an equation for this parabola, and then we're going to find out how deep is this dish, because the depth and the focus are not at the same place. Okay, so when you read this, it says the sun's rays are reflected from the mirrors towards 2 boilers located at the focus. So this boiler is the focus of the equation, and it is 10 feet away from the surface of the parabola that's used to collect the solar energy. So the beams are coming to it and going towards the boiler. It's hard to say. Okay, so we've got 2 things going on here. I'm going to go ahead and draw in an axis here and here. And this point is the vertex. And the vertex, for the sake of simplicity, is going to be at 0, 0. So that would make the focus at the point 0, 10. And so from this, I know P. P is 10. I don't need the directrix in this particular problem. So I'm looking at A, and I'm looking at writing something with the vertex at 0, 0. It opens up, so it's x squared equals 4py. So x squared equals, I know what p is 10, so my equation is x squared equals 40y. So that's part A. Now I need the depth. So if I make a point right here, notice I still have, this is my x-axis and my y-axis. This point here has a x-coordinate and a y-coordinate, and one of which I do know. I do know what the x-coordinate is. The x-coordinate is going to be half of 37, right, because it's 37 from here to here, so this is half, but I don't know what the depth is, so I need the y-coordinate. Well, I've written the point right next to the equation, so I know what x is, so I put in 37 halves. I'm going to erase this piece I can't erase that piece. That's not a minus. There. Squared is equal to 40y. Now, when you take 37 divided by 2 squared, and then divide that by 40, y is going to be approximately 8.6 feet. And that is B. So remembering that this is a point, setting up the problem so that it makes it in the easiest possible way, putting the vertex at 0, 0, we can come up with a reasonable equation for this. So here are a few examples for you. There are plenty more. We'll be doing some of these problems in class and working several other applications of a parabolic shape. And so I'll see you then.